In mathematics, a normal number is a real number whose infinite sequence of digits in every base b is distributed uniformly in the sense that each of the b-digit values has the same natural density 1, b. Also, all possible b2 pairs of digits are equally likely with density b-2, all b3 triplets of digits equally likely with density b-3, etc. Intuitively, this means that no digit, or combination of digits, occurs more frequently than any other. And this is true whether the number is written in base 10, binary, or any other base. A normal number can be thought of as an infinite sequence of coin flips or rolls of a die, even though there will be sequences such as 10, 100, or more consecutive tails or fives, or even 10, 100, or more repetitions of a sequence such as tail head or 6 to 1. There will also be equally many of any other sequence of equal length. No digit or sequence is favored. While a general proof can be given that almost all real numbers are normal, this proof is not constructive and only very few specific numbers have been shown to be normal. For example, it is widely believed that the numbers square root 2, pi, and e are normal, but a proof remains elusive. Definitions. Let sigma be a finite alphabet of b-digits, and sigma infinity the set of all sequences that may be drawn from that alphabet. Let S sigma infinity be such a sequence. For each or in sigma, let ns denote the number of times the letter A appears in the first n digits of the sequence S. We say that S is simply normal if the limit for each A. Now let W be any finite string in sigma, and let ns to be the number of times the string W appears as a substring in the first n digits of the sequence S. Equals 3. S is normal if, for all finite strings W sigma, where W denotes the length of the string W. In other words, S is normal if all strings of equal length occur with equal asymptotic frequency. For example, in a normal binary sequence, 0 and 1 each occur with frequency 1/2, 00, 01, 10, and 11 each occur with frequency 1/4, 000, 001, 010, 011, 100, 101, 110, and 111 each occur with frequency 1/8, etc. Roughly speaking, the probability of finding the string W in any given position in S is precisely that expected if the sequence had been produced at random. Suppose now that B is an integer greater than 1 and X is a real number. Consider the infinite digit sequence expansion Sx b of x in the base b positional number system. We say that x is simply normal in base b if the sequence Sx b is simply normal, and that x is normal in base b if the sequence Sx b is normal. The number x is called a normal number if it is normal in base b for every integer b greater than 1. A given infinite sequence is either normal or not normal, whereas a real number, having a different base b expansion for each integer b2, may be normal in one base but not in another. For bases R and S with log R, log S rational, every number normal in base R is normal in base S. For bases R and S with log R, log S irrational, there are uncountably many numbers normal in each base but not the other. A disjunctive sequence is a sequence in which every finite string appears. A normal sequence is disjunctive, but a disjunctive sequence need not be normal. A rich number in base B is one whose expansion in base B is disjunctive. One that is disjunctive to every base is called absolutely disjunctive or is said to be a lexicon. A number normal in base B is rich in base B, but not necessarily conversely. The real number x is rich in base b if and only if the set xbn mod 1, nn, is dense in the unit interval. We defined a number to be simply normal in base b if each individual digit appears with frequency 1, b. For a given base b, a number can be simply normal, b dense, normal, or none of these. A number is absolutely non-normal or absolutely abnormal if it is not simply normal in any base. Properties and examples. The concept of a normal number was introduced by Emil Borel in 1909. Using the Borel-Cantelli lemma, he proved the normal number theorem. Almost all real numbers are normal, in the sense that the set of non-normal numbers has Lebesgue measure 0. This theorem established the existence of normal numbers. In 1917, Vatswif-Sierpinski showed that it is possible to specify a particular such number. Beecher and Figueira proved in 2002 that there is a computable absolutely normal number, however no digits of their number are known. The set of non-normal numbers, though small, in the sense of being a null set, is large, in the sense of being uncountable. For instance, there are uncountably many numbers whose decimal expansion does not contain the digit 5, and none of these are normal. Champernowne's number 0.12345678911121314151617, obtained by concatenating the decimal representations of the natural numbers in order, is normal in base 10, but it might not be normal in some other bases. The Copland-Urdos constant 0.2357111317192329313141443, obtained by concatenating the prime numbers in base 10, is normal in base 10, as proved by Copeland and Urdos. More generally, the latter authors proved that the real number represented in base B by the concatenation 0.fff, where f is the nth prime expressed in base B, is normal in base B. Besikovich proved that the number represented by the same expression, with f equals n2, 0.1491625364964811001211144, obtained by concatenating the square numbers in base 10, is normal in base 10. Davenport and Urdos proved that the number represented by the same expression, with f being any polynomial whose values on the positive integers are positive integers, expressed in base 10, is normal in base 10. Nakai and Shiyokama proved that if f is any non-constant polynomial with real coefficients such that f greater than 0 for all x greater than 0, then the real number represented by the concatenation 0, where f is the integer part of f expressed in base b, is normal in base b. The authors also show that the same result holds even more generally when f is any function of the form f equals alpha x beta plus alpha 1 x beta 1 plus alpha the dx beta d, where the alpha s and beta s are real numbers with beta greater than beta 1 greater than beta 2 greater than beta d0, and f greater than 0 for all x greater than 0. Every Chaitin's constant is a normal number. A computable normal number was constructed in. Although these constructions do not directly give the digits of the numbers constructed, the second shows that it is possible in principle to enumerate all the digits of a particular normal number. Bailey and Crandall show an explicit uncountably infinite class of B normal numbers by perturbing Stoneham numbers. It has been an elusive goal to prove the normality of numbers which were not explicitly constructed for the purpose. It is for instance unknown whether square root 2 pi ln or e is normal. It is not even known whether all digits occur infinitely often in the decimal expansions of those constants. In particular, the popular claim that every string of numbers eventually occurs in pi is not known to be true. It has been conjectured that every irrational algebraic number is normal, while no counterexamples are known. There also exists no algebraic number that has been proven to be normal in any base. Non-normal numbers. No rational number is normal to any base, since the digit sequences of rational numbers are eventually periodic. Martin 2001 has given a simple example of an irrational absolutely non-normal number. Let D2 equals 4 and then she is absolutely non-normal and a Liouville number, hence a transcendental number. Properties. Additional properties of normal numbers include: every positive number x is the product of two normal numbers. For instance, if y is chosen uniformly at random from the interval, then almost surely y and y are both normal, and the product is x. If x is normal in base b and q0 is a rational number, then is normal in base b. From this it follows that Champonone's number is normal in base 10 and that the Copland-Urdos constant is normal in base 10. A sequence is normal if and only if every block of equal length appears with equal frequency. This was implicit in the work of Ziv and Lempel and made explicit in the work of Burke, Hitchcock, and Vinod-Chandran. A number is normal in base b if and only if it is simply normal in base bk for every integer. This follows from the previous block characterization of normality. Since the nth block of length k in its base b expansion corresponds to the nth digit in its base bk expansion, a number is simply normal in base bk if and only if blocks of length k appear in its base b expansion with equal frequency. A number is normal if and only if it is simply normal in every base. This follows from the previous characterization of base B normality. A number is B normal if and only if there exists a set of positive integers where the number is simply normal to bases Bm for all no finite set. Suffices to show that the number is B normal. The set of normal sequences is closed under finite variations. Adding, removing, or changing a finite number of digits in any normal sequence leaves it normal. Connection to finite state machines. Agafonov showed an early connection between finite state machines and normal sequences. Every infinite subsequence selected from a normal sequence by a regular language is also normal. In other words, if one runs a finite state machine on a normal sequence, where each of the finite state machine's states are labeled either output or no output, and the machine outputs the digit it reads next after entering an output state, but does not output the next digit after entering no output state, then the sequence it outputs will be normal. A deeper connection exists with finite state gamblers and information lossless finite state compressors. A finite state gambler is a finite state machine over a finite alphabet, each of whose states is labeled with percentages of money to bet on each digit in. For instance, for an FSG over the binary alphabet, the current state Q bets some percentage of the gambler's money on the bit 0, and the remaining fraction of the gambler's money on the bit 1. The money bet on the digit that comes next in the input is multiplied by, and the rest of the money is lost. After the bit is read, the FSG transitions to the next state according to the input it received. FSGD succeeds on an infinite sequence S if, starting from $1, it makes unbounded money betting on the sequence, i.e., if, whereas the amount of money the gambler D has after reading the first n digits of S. A finite state compressor is a finite state machine with output strings labeling its state transitions, including possibly the empty string. In other words, for a finite state compressor C with state set Q, C is information lossless if the function mapping the input string of C to the output string and final state of C is 1-to-1. Compression techniques such as Huffman coding or Shannon-Fano coding can be implemented with ILFSCs. An ILFSCC compresses an infinite sequence S if, whereas the number of digits output by C after reading the first n digits of S. Note that the compression ratio can always be made to equal 1 by the one-state ILFSC that simply copies its input to the output. Schnorr and Stim showed that no FSG can succeed on any normal sequence, and Burke, Hitchcock and Vinod-Chandran showed the converse. Therefore, a sequence is normal if and only if there is no finite state gambler that succeeds on it. Ziv and Lempel showed. A sequence is normal if and only if it is incompressible by any information lossless finite state compressor. Since the LZ compression algorithm compresses asymptotically as well as any ILFSC, this means that the LZ compression algorithm can compress any non-normal sequence. These characterizations of normal sequences can be interpreted to mean that normal equals finite state random, i.e., the normal sequences are precisely those that appear random to any finite state machine. Compare this with the algorithmically random sequences, which are those infinite sequences that appear random to any algorithm. Connection to equidistributed sequences. A number x is normal in base B if and only if the sequence is equidistributed modulo 1, or equivalently, using Weyls' criterion, if and only if this connection leads to the terminology that x is normal in base beta for any real number beta if the sequence is equidistributed modulo 1.